The coefficient of determination. Sums of squares in regression. When we have our regression line, we look at the data point as it compares to the regression line. Our data point we're calling x sub 1, y sub 1. So for a value x sub I, we have our observed value of the response variable y sub I. We can use our formula y hat to find the predicted value of the response variable y hat sub I. Then we can take the mean of the observed values of the response variable, which is y bar. The distance between y sub I and y hat sub I is a deviation not explained by the regression. If we look at the distance between the value we find from our formula, which is called y hat sub I, and the mean of the observed values, y bar, that deviation is explained by the regression. The distance between our observed value, y sub I, and the mean of the observed values, y bar, that is the deviation of the observed y value from the mean. We need those values so we can find the total sum of squares, which is abbreviated as SST. That's the total variation in the observed values of the response variable. SST equals the sum of, in parentheses, y sub I minus y bar, close parentheses, squared. Regression sum of the squares, abbreviated as SSR. The variation in the observed values of the response variable explained by the regression. SSR equals the sum of, in parentheses, y hat sub I minus y bar, parentheses, squared. Error sum of squares, SSE. The variation in the observed values of the response variable not explained by the regression. SSE equals the sum of y sub I minus y hat sub I, parentheses, squared. Coefficient of determination. The coefficient of determination, R squared, is the proportion of variation in the observed values of the response variable explained by the regression. Thus, R squared equals SSR divided by SST. The coefficient of determination, R squared, always lies between 0 and 1. A value of R squared near 0 suggests that the regression equation is not very useful for making predictions. A value of R squared near 1 suggests that the regression equation is very useful for making predictions. Regression identity. The total sum of squares equals the regression sum of squares plus the error sum of squares. SST equals SSR plus SSE. Computing formulas for the sum of squares. The computing formulas for the three sums of squares are: to find SST, that equals the sum of y sub I squared minus parentheses sum of y sub I, close parentheses, squared divided by n. SSR equals, in brackets, the sum of x sub I times y sub I minus the sum of x sub I times the sum of y sub I divided by n, close bracket, squared, all over the sum of x sub I squared minus, in parentheses, the sum of x sub I, close parentheses, squared divided by n. And SSE equals SST minus SSR. Example. For the particular regression analysis, SST equals 175.4223 and SSR equals 170.4916. We want to obtain the coefficient of determination and find SSE. Our formula for the coefficient of determination, r squared equals SSR divided by SST. So we substitute and have 170.4916 divided by 175.4223. That equals, with 4 decimal places, 0.9719. To find SSE, that equals SST minus SSR. Substituting, I have 175.4223 minus 170.4961, which gives us a result of 4.9307. Example: a study on the relationship between the estradiol levels of pregnant women and the birth weights of their children is given in the table. Here, X denotes estradiol level in milligrams per 24 hours, and Y denotes birth weight in hectograms. When X is 15, Y is 31. When X is 25, Y is 38. When X is 21, Y is 30. When X is 18, Y is 38. When X is 27, Y is 39. When X is 12, Y is 27. When X is 19, Y is 37. When X is 16, Y is 29. Decide whether finding a regression line for the data is reasonable. To do this, we want to see what our data looks like when graphed. Moving to our calculator, we want to go to Stat, Edit, and I'm going to type my values for X in L1. 15, 25, 21, 18, 27, 12, 19, 16. Next, I want to fill in my data for L2. 31, 38, 30, 38, 39, 27, 37, 29. We want to see what a graph looks like of this data set. Before I go to graph, I just want to double check y equals, I don't have an equation in y1, and plot 1 is on. I can tell plot 1 is on from here because it is highlighted. Otherwise, what I could do is I could go to stat plot, which is second y equals, and I see that it is on. Zoom stat will give me the best fit for my data, and it looks like I can draw a line through this data set. There is a linear pattern to the data, so it is appropriate to carry out a linear regression. Continuing with our example, we now want to compute the coefficient of determination, which is r squared. We want to do this in our calculator. In order to calculate the coefficient of determination, I need to have my data in L1 and L2, which I do. Second, quit gets me out of my graph. In order to find my coefficient of determination, first I need to make sure I have my stat diagnostics turned on. One way to find that is by going to Mode, arrowing down to Stat Diagnostics, arrow over to On, and then press Enter. If you've gone to Mode and Stat Diagnostics isn't listed there, our other option is second and my 0, which is Catalog. I arrow down until I get to the D. Every function in our calculator is listed here. I stop once I find Diagnostic On. enter, enter again, and it also turns on the stat diagnostics. Now I want to go to stat, over to calc, and I'm going to choose for linear regression AX plus B. My X list is in L1, my Y list is in L2. I don't have a frequency list. And we can store our equation in L1 if we want to. I'm not going to this time, and I'm just going to go to calculate. If you do not have the stat wizard, then you would just type, after you see LINREG parenthesis L1 comma L2. Enter. And since I turned on the stat diagnostics, not only do I have A and B, I also have R squared and R. Right now, we're concerned about R squared. I want to round that to 4 decimal places. Which gives me 0.5622. Determine the percentage of variation in the observed values of the response variable explained by the regression and interpret your answer. To find my percentage of variation, all I have to do is take my coefficient of determination and change it to a percent. 0.5622 becomes 56.22%. The regression equation is moderately useful for making predictions. This is because 0.5622 is halfway between 0 and 1, where 1 has a strong linear regression and 0 has no linear regression. Example. Following are age and price data for 8 randomly selected ambulances between 1 and 6 years old. Here, X denotes age in years and Y denotes price in hundreds of dollars. When X is 6, Y is 270. When X is 1, Y is 420. When X is 6, Y is 265. When X is 2, Y is 350. When X is 6, Y is 250. When X is 2, Y is 355. When X is 4, Y is 310. When X is 5, Y is 290. Decide whether finding a regression line for the data is reasonable. We need to see what the data looks like. Heading to my calculator, Stat, Edit, and type in our data set. I want to put X in L1, so I have 6, 1, 6, 2, 6, 2, 4, 5. Moving over to L2, I type in the Y values, 270, 420, 265, 350, 250, 355, 310, and 290. Again, making sure we have our stat plot on and that we do not have a line in Y equals, I can go to Zoom, and I want Zoom Stat, which is 9. And here I have my data points. They look like they make a line. There is a linear pattern to the data, so it is appropriate to carry out a linear regression. Compute the coefficient of determination. That is R squared. Going back to our calculator, Stat, over to Calc, want to use number 4, linear regression, second L1, comma, second L2. I don't need to store the equation, so I'm just going to press enter. I want to use 4 decimal places. R squared equals 0.9412. Determine the percentage of variation in the observed values of the response variable explained by the regression and interpret your answer. So I want to change this to a percent. 94.12%. The regression equation is very useful for making predictions. Recapping the section, the coefficient of determination is R squared, and it is always between 0 and 1. If the value of R squared is near 0, that suggests the regression equation is not very useful in making predictions. If the value of R squared is near 1, that suggests the regression equation may be very useful in making predictions. The regression identity says that the total sum of squares equals the regression sum of squares plus the error sum of squares.